Hello there. This is the third in our video series on building a datascope so that we can figure out how the sound system works on a Bally pinball machine so that we can build our own sound card. So in this video I'm going to be showing you how I actually built the datascope, and this is probably going to be the shortest and simplest of the first three videos that I'm doing. I built a datascope a long time ago, and it was a 27 channel datascope, and this is what it looks like. Now the card is an STM32 103 VET6, I believe. I could be wrong about the number. I'll put it down below or something. Anyway, got it off of Amazon. Currently not available, but there are other ones out there with the same chip on it. The big thing about this chip is that it has quite a bit more memory than the STM32 Blue Pill does, and it has a lot more pins. The datascope is simply pins connected to a connector that I can plug into the board. So for my 6-channel datascope, I just used the first 6 lines on here plus the ground line, because you always have to have a ground line. And that's it. So I'm going to show you a little schematic of this card, and then I'm going to show you the code that makes it work, and it's really simple. So anyway, let's get right to the schematic. Okay, here's the schematic. I just knocked this together to kind of give you an indication of what we're using on the processor. This isn't an actual schematic of the board I have. It's just a representation. Don't try to build this. It won't work. But it's going to show you how little bit of this processor I am actually using for this 6-line datascope. So I use the D0 through D5 input lines to input my data on. I have a common ground line, so that makes my datascope connection to my device. Now, this is an STM32 F103 VET6. And the one really nice thing about this is that even though it is a 3.3 volt processor, almost every pin on here is 5 volt tolerant. You should look at the data sheet to make sure that the pins you want to use are 5 volt tolerant, but since the Bally pinball machine puts out 5 volt signals, you either need to use a 5 volt tolerant processor or add some level converters to convert it down. And the only other thing I use on this chip is the USB connection, which I believe comes off of PA 11 and 12, and it goes out to the USB port. And so what I do is I read in the data on this port until I fill up all the memory, then I dump it to the USB, and then I start over again. So that's it. Actually, I guess I should show one other thing that I didn't on this, and that is my little processor board has a switch. I don't remember which pin it's on. We'll see it in the code. And I actually hold my capture until I press that switch. And then once I press the switch, I start the capture and I run through until it's full. I dump the data and I stop the capture. And that's it. It's a simple little thing. So let's go over and take a look at the code. Okay, here is the code for the 6-line datascope. I start off by defining a buffer count of 26,000. Now I played around with this count until I got a buffer size that I thought was adequate for what I wanted to do. but left me enough memory to get the rest of the work done. Anyway, then I actually defined a 16-bit buffer of that count, and that's where my data will get stored. I also create a couple of variables, start and stop, and they're long, so I can, or unsigned long, so I can put the time in that I start and stop my capture. I set up a couple of variables that I'm going to use to hold the counts, and like the sample count for each sample when I'm reading, and then a total sample count for all the samples taken in the entire capture. I define a deregister variable. I'm going to be doing register level I/O instead of port I/O, so I'm going to read in a whole register. So I define a variable to read that register into. A couple of uh, variables to keep track of the data that I'm reading in for doing my comparisons with, and that's all I need for variables. And then in the setup, I simply go in, I set the pin mode for the pins I'm going to be using as inputs to input pull up. Sometimes that's a little dicey if you have a 3.3 volt machine and you're using a 5-volt line, but I haven't seemed to have any problem with it. The way the uh, Bally machine works, there's a lot of resistive dividers and stuff that actually bring the voltages down a lot lower, uh, and they pull the line to ground to activate it. So I wanted that line to be cleanly high when it wasn't activated, so I used the pull-up function. I enable serial and output the word Datascope, and then I delay a couple seconds just to give it time. So in my loop, the first thing I do is output a high on PC0, which is the LED line on this board. And then I set the switch variable to a 1, which is the default value for switch. And then while switch stays at 1, I just continuously read the switch value coming from my board on PC1. So I'm going to hang right here and not go any farther until the switch on the board is pressed. And then once it's pressed, I drop down in and start my sampling. So I turn off the LED. That indicates that I saw the switch. I set the starts value to the current millisecond. I clear out the sample counts, and then I do the read data function. And that read data function is going to read until the buffer is full. And once the buffer is full, I do the send data function. I delay about 5 seconds, and I loop back up, turn the light back on, and indicate that I'm ready to do another capture whenever you push the button. So the read function is a very simple little function. It starts off, remember sample count was set to 0 up above, and the buffer count is at 26,000 I set up at the very beginning. And so I look and say, while the sample count is less than the buffer count, I read the value that's in the D register. So that's the nomenclature for reading in the whole D register, 16-bit register in one read, and putting it in the variable D register. Then I take the D register and I AND it with a 3F because I only want the lower 6 bits, and toss that into the T variable just to hold it. Then I compare to see if T1 is equal to T2. If they're the same, then nothing has changed. So I just increment the count. The total count is just incremented. It started off at 0, so the count would go to 1. And then I check to see if the total count is greater than 3FF, because 3FF is the maximum count that I can store in the remaining 10 bits. An F is 4 bits, so that's 4, 4, and 3 is 2 bits, so that's 10 bits worth of of count. So if the count has gotten that big, I go to the next buffer. So basically I write the data out, or I store the data and I create a new buffer. If T1 is not equal to T2, I immediately go to the next buffer regardless of what the count is, and then I set T2 to T1. So now T2 is holding whatever my last read was. After I save the data or save the count, depending on what the case is, I delay for a microsecond. I just did that because I wanted to actually get a longer capture time, and I didn't need the tightest resolution that this thing could capture. So by adding the 1 microsecond delay and 26,000 buffer locations with all the repeat counts from the duplicates would give me a total of up to about 50 seconds worth of capture time. And that's what I wanted. Now, if or when the buffer count equals, when the sample count equals the buffer count, we stop capturing and we set the stop time to whatever the current millis is at that stop time. Now in the next buffer thing, I remember up here I said if whenever you or either you fill the time, so if the total count is 3FF, or if the data has changed, you go to the next buffer, and that's simply taking the sample count, which is the pointer to the current sample we're working on, and you take the total count shifted to the left 6 places and add the, or it with the T2, which is the value that you've been capturing. You increment the total samples. I'm sorry, you increment the sample count, and then you add however many samples you got to the total samples, and you clear the current counter and start over again and start doing the next input. Now, once you're done, again, all the way up here on top, so once that read data ends, which happens right here, right after that, the read ends, then you do a send, and the send is even simpler, I guess. We're going to define a couple of hex strings, then we're going to print out start and the value that's in the start value. And once we've got the start time recorded, then we're going to step through our buffer, and we're going to step by 8 because we're going to put 8 values on each line. So we're going to start at 0 and go until we get to the end of the buffer count, 26,000, and we're going to step by 8. We're going to print out a D followed by a space, and this is simply adding leading 0. So if I is 0 or I is 1 or up to 9, we're going to output, if I is less than 10,000, we output 1 0. If I is less than 1,000, we output another 0. If I is less than 100, we put out another 0. And if I is less than 10, we put out another 0. And then we print I. And what that does is simply pad the beginning of the number with extra zeros so that all the data lines up. It's simply there to make it more pleasant to read. We print a space. So I is a pointer to the location in memory that we are printing out. And so we print out that I with its leading zeros and a space. And then we need to print out 8 hex strings. So this loop right through here steps through 8 locations, creating a hex string out of each location and printing out that hex string with the space. and then at the very end of it, it just does a print line to make a new line, delays for 1 millisecond just to give the output time to output that data, and then it repeats it again. And then when you get all done with that, you print out the stop and the stop variable. You print the milliseconds count, the total sample count, and that's the end. Now, to use this Datascope, you have to actually use something like some terminal program that has logging capabilities that can capture this string and log it. You can read it just using the Arduino IDE's terminal function, but I normally use Teleterm or something like that and I set up a log and I capture it using that. That's it. That's the Datascope in a nutshell. Now, the next time I go down to the shop, I will record doing a capture just so you can see how this capture actually works. And I'll probably hold off on publishing this until I get that capture, and I will add it on to the end of this. Okay, I am back down at Mike's shop. This is actually take 2 of this recording because the last one I made some mistakes and it didn't work. So let me show you what I have here. Here's the sound card that I'm going to be working with, and I have already soldered some wires to the input pins coming into the sound card so that I can capture that data. And here's the Datascope. I showed that to you the other day, and I'm just going to hook up the first 6 lines to these 6 lines and hook the ground line to ground, and then I'm going to hook the other end up to my laptop, and then I'll bring you back and show you what that looks like. Okay, as you can see, I have those jumpers connected up to the first 6 lines of my Datascope. The blue jumper here is connecting ground to the chassis ground of the unit, and now I'm going to plug this into my laptop and set up my laptop so it can capture the data, and I'll show you how I do that. Okay, I am using a program called Teleterm to capture the data that's coming in here. Pretty much any terminal emulator that has a logging capability will work fine for this. This just happens to be one that I have. So I'm going to go under File, Log, and set up a log location. It's set to desktop, that's fine. I'll change my name. I'm just going to call this 1111 today. .log. And I hit save, and now everything that comes in on this terminal will be logged into that file. Okay, I have my machine powered on. I haven't started a capture yet. The last time I did this, I tried to use the flippers as my no sound solenoid, so I could capture a solenoid being activated without a sound being created. As it turns out, though, the solenoids for the flippers don't go through the solenoid driver board, so that didn't work at all. So what I'm going to be doing is I'm going to be capturing the sound from this saucer. And I want to show you what's going to happen. I'm going to activate the saucer. It's going to play some sounds. And then it's going to eject the ball. But when it ejects the ball, there's no more sounds. So you can hear it played a few sounds beforehand. And then it ejected the ball. And so that's what I want to capture. And to make this as simple as possible, I'm going to do this one time. So the only thing on the capture is that sequence of sounds and then the ejection of the solenoid. And that's all I want in this first capture. So now on my capture board, there's a little switch that activates the capture. And I hope you can see this zoomed out this far, but the yellow light just came on showing that this thing is capturing, and it will capture for about 50 seconds. So I just finished capturing that data. Now I'm going to try to move you back over here to the screen before the 50 seconds runs out, and hopefully you can see that. So as soon as my 50 seconds finishes, it should dump the data to this screen. And there it goes. And that's it. The capture has completed. I have gotten my information in, and now I can take this back home and analyze that to see what it looks like. And that is all I am doing today. So I will stick this on the end of the other video, and you guys can see what it looks like. Okay, and just to wrap things up, here is my Datascope display program, and I'm going to go ahead and load that file. I've moved it onto a memory stick. There it is, 1111.log, and I will open that up. And you can see that there is my capture with the one event. So here is my data. Data file's about 50 seconds long roughly, and right there is that one event that I triggered. So let me jump into here and zoom in some. So you can see that up until here, the strobe line was sitting low, but the first four data lines, 1, 2, 3, 4, were all sitting high. In that state, nothing is happening because the low strobe is selecting the solenoids, but the four high states is saying no solenoid because that state is not valid. But then right here, the thing transitions to a high, so no solenoids can be selected at all, and whatever sound this is, which is a 0110, so a sound of 6, because that's actually 0248. Oh, that's, and the last one's a 0216. Okay, so anyway, that's 2 and 4 high, so that's a sound of 6 gets played there. And then we jump to right here, and we'll zoom in. Okay, and so at this point right there, the thing is low, but again, the 4 solenoid lines are high, so no solenoids being fired. And then on the transition, right after this, we have again we have a 0, 0, 8, or 0, 2, 4, and 8. So that's a tone of 12 being played. And then right here is the next tone. And it plays after the transition. So that's 0, 0, 4, and 8. So that's another tone of 12. And then there, is a low, low, high, high, low. So that's another tone of 12. So that was 3 12s in a row. And then we have a long gap. And then right here, the strobe goes low. And some lines are low, so 0, 0, 0, 1. So solenoid 0, 2, 4, 8. Solenoid 8 is being fired. And then after that, all the lines go high, but the strobe line does not return up. It stays low. And since the strobe line doesn't transition from a low to a high, no sound is being played. So that's the key to how this thing can play a sound or a solenoid interchangeably. It's the solenoid. The strobe line is really just a level enable, so as long as it's low, if you put a valid number between 0 and 14 in here, it'll fire that solenoid, but if you put a 15 in there, it doesn't do anything. So if you don't want to fire a solenoid, you put a 15 there. When a transition occurs, then a sound will be played. So if you don't want a sound after a solenoid, you just don't transition the strobe line back up to the high position. You just leave it low until you're ready to fire another solenoid. So that answers that question. That was the question I had, was how do you fire a solenoid and not make a sound? The solenoid doesn't need a transition, so that works. So that's what I was trying to find out. I've accomplished that. I've got all the data that I think I need now. So that's going to end this video. Thanks a lot for watching, guys.